day guys, and welcome to the Success Blueprint YouTube channel. Please, if you are new to the channel, consider to subscribe because this channel will be of great help to you, particularly to those of you advanced level students who will be sitting for your GC examination 2025. So today we'll be looking at the Southwest Regional Mock Examination 2025, particularly advanced level physics paper 2 0780. Now to the left of my dashboard, I have the question paper. This question paper was written on Friday, 21st of March, 2025 afternoon session, and it was written for 3 hours. Instructions to candidate. Please consider reading your instructions vividly because it gives you a clue of how to go about the questions. So this question paper was divided into section 1, section 2, and section 3. Section 1 was designed to be answered in 1 hour 30 minutes, section 2 in 40 minutes, and section 3 in 50 minutes. All this compounds to 3 hours. The paper also says calculators and formula booklets are allowed. Without wasting much of your time, let's get straight to business. So in section 1, it says we should answer all the questions. Question 1 reads: a communication satellite occupies a parking orbit around the Earth such that the radius r0 of the orbit is given by the cube root of gmt squared over 4 pi squared, where t is the period of revolution of the satellite, g is the universal gravitational constant, and m is the mass of the Earth. Okay, so A, determine the base units of g. B, calculate r0, the radius of the orbit. And C, hence calculate the height h of the satellite above the Earth's surface and state any assumption made in your calculation. Take note, the period of rotation of the Earth about its axis is 24 hours. Okay, so looking at, we'll start directly with section 1. Okay, so section 1, question 1. Voila. So in this particular question, we've been given the formula r0 equals to the cube root of gmt squared divided by 4 pi squared. Take note, if you are not smart enough, you discover what this question is gotten when you relate Newton's law of universal gravitation with Kepler's third law of planetary motion. That is Kepler's law of period. Okay, well, let's keep that aside. So if this equation is homogeneous, then rearranging the equation, the arranged form of the equation will also be homogeneous. So if I decide to cube both sides, I'm going to have r0 cube will be equals to the cube of the cube root takes care of themselves. So I'm going to have gmt squared divided by 4 pi squared, which gives me g to be equals to 4 pi squared times r0 cube divided by mt squared. So since this equation was homogeneous, then this will also be homogeneous. So suppose equation star is homogeneous, then it suffices that what the base units of g will be equal to the base units of the right hand side. So I'm going to write the base units of g will be equal to the base units of r cube, base unit of r0, all this cube, divided by the base units of m, times the base units of t, all this squared. Take note, I've ignored 4 pi squared because it is simply a dimensionless constant, and whenever a parameter is dimensionless, its base unit is assumed to be 1. So if this is the case, since r0 represents the radius of the orbital path, it means it is measured in meters since it represents length. M is mass measured in kilograms, and t is time, orbital period measured in seconds. So the base units of g will reduce to meter cube divided by kilograms times seconds to the power 2. Rearranging, starting from mass going to length and time, I'm going to have per kilograms meter cube per second squared, and these are the base units of the constant G. That's it. Now B says let's calculate R0, the radius of the orbit. Now let's suppose we have the Earth. Okay, let's say we have the Earth and the satellite is orbiting the Earth. So let's have this sketch below. Let's suppose we have, this is our Earth, this is the Earth of mass M, capital M. The center of the Earth is somewhere here. Distance from the center to the surface is, of course, the radius of the Earth. And then we have an orbital space, an orbital path, where there is, on this orbital path, we have our satellite. Okay, this is our satellite. This is satellite of mass small m. Now, the distance from the surface of the Earth to this height, to that altitude, is the height h. Now, but the value of R0 represents the distance from the center of the Earth right up to that altitude. That is R0. Okay, so if that's R0, to quickly get the value of R0, we'll just apply our formula given to us. So applying the formula, we had R0 being equal to the cube root of G mt squared divided by 4 pi squared. Take note, the value of G, the gravitational constant, is 6.67 times 10 to the power negative 11 Newton meter squared per kilogram squared. The value of the mass of the Earth gotten from the formula booklet is 6.0 times 10 to the power 24 kilograms. And the period, we're being told in the question that the period of revolution, the period of rotation of the satellite above the Earth, is 24 hours. So since R is length in meters, so we're going to have all our parameters in SI units. And in 24 hours, if T is 24 hours in seconds, this will be 24 times 3,600 seconds, because in 1 hour there are 3,600 seconds. This will boil down to 86400 seconds. So that will be our period in seconds. Keying all of this down in this formula, we're going to have this to be equal to the cube root of 6.67 exponent negative 11, ignoring the unit, times 6.0 times 10 to the power 24 times 86,400 squared divided by 4 pi squared. If you quickly use a calculator, this will give us R0 to be equals to R0 will be equals to 4229753.86. This is to 2 decimal places. In standard values, this will be approximately equals to 4.23 times 10 to the power 7 meters. 10 meters is in meters, so that will be our value of R0. Next, it says let's calculate the height of the satellite above the Earth's surface. Okay, now from this our sketch up here, since R0 is equals to this and this combined, we can write that Roman 3. We can say that R0 is equals to the radius of the Earth plus the altitude above the height above the Earth's surface. Remember that value of h was given in capital letters, so this implies that h will be equals to r0 minus re. Now this, take note, the radius of the Earth from your formula booklet, the radius of the Earth is approximately 6.4 times 10 to the power 6 meters. So with this value of the radius of the Earth, we are going to have that altitude h to be equals to, the altitude h will be 6.23 10 to the power 7 meters minus 6.4 times 10 to the power 6 meters. If you quickly use your calculator, you are going to have h to be approximately equals to, that value of h will give us 3.63 times 10 to the power 7 meters, and that is the height above the Earth. As for the assumption, it says you should also state any assumption made in your calculations. Now, if this satellite is orbiting the Earth and its period of rotation is 24 hours, which is the same as the period of rotation of the Earth, it means that we assume that the satellite is in geosynchronous orbit. Geosynchronous orbit is simply the orbit of any satellite when viewed from the Earth. Why is this so? Because an observer standing on the Earth's surface will see the satellite to be at the same position at all times. That is because the rotation of the satellite and that of the Earth is the same with time. So the satellite is in geosynchronous orbit. So C, we assume, assumption made, so we assume the satellite is in geosynchronous orbit. In geosynchronous orbit, since its period, that is its period of rotation, is the same as that of the Earth. Okay, that said, we are done with question 1. Now question 2, it reads 2a, state Newton's second law of motion. B, a bus of mass 3.0 times 10 to the power 3 kilograms runs into an electric pole when moving at a speed of 4 meters per second, and it is brought to rest in 2 seconds. Okay, Roman 1, calculate the force the electric pole exerts to bring the bus to rest. And Roman 2, sketch a graph to show how the impact force varies with time during the entire collision. Okay, so question 2. Now, according to Newton's, he stated that, according to Newton's second law in particular, he stated that the rate of change of linear momentum is directly proportional to the applied force and takes place in the direction of the force. Writing this down, I'm going to write Newton's second law. Newton's second law states that the rate of change of linear momentum is directly proportional to the applied force. And takes place in the direction of the force. Note, you could also state this mathematically by generally writing F is equals to MA. But in this case, you have to define your terms. So you say where F is the applied force, M is the mass of the object, and A is the acceleration of the object. So this is the mathematical statement. Okay, so we are done with A. So in B, Roman 1, we have to calculate the force the electric pole exerts to bring the bus to rest. So in this case, we are going to relate Newton's second law with impulse. Okay, what is impulse? Impulse is simply the product of the force and the time in which the force is acting. Whenever two bodies collide, the force one body exerts on the other multiplied by the time they spend together in contact gives us impulse. So in that case, we are going to have from impulse generally represented by I, or you say G, which is equals to the force time. And take note, this impulse is the same as the change in momentum. The change in the momentum of a body. Okay. So this will be the same as the mass times the final velocity minus the initial velocity, because momentum is normally the product of mass and velocity. So a change in momentum will be the mass times the change in velocity. So if this is the case, we are going to have that the force F times the time will be equals to M times V minus U, which means that F is going to be M times V minus U divided by that time T. Now, according to the equation, they gave us the mass of the body and they gave us the speed with which the body collides with the electric pole. So take note, in this case, we are going to have magnitude values, okay, because the final speed of the body is normally 0, while the initial speed is this given to us in the equation. So here we're going to have change in magnitude values. So we have magnitude values as here and here as well. So if that's the case, with the mass given to us to be 3.0 times 10 to the power 3 kilograms, and the final velocity of the object being 0, of which the initial velocity is 4 meters per second, and the time t is 2 seconds, this will mean that the force will be equals to the mass 3.0 times 10 to the power 3 kilograms times the difference in the velocities. So we're going to have 0 minus 4, all this in meters per second, divided by this time 2 seconds magnitude value. So this will reduce to the force being equals to F, the force being equals to approximately 6.0 times 10 to the power 3 newtons. That is approximately 6 kilo newtons in terms of 10, multiples of 10. Okay, so Roman 2, it says sketch a graph to show how the impact force varies with time during the entire motion. Now, for the graph of force against time, we have this. We have our force in the y-axis and time in the x-axis. So we have here force in newtons and time in seconds. Normally, during impulse, the graph of force against time normally looks like this, wherein as time before impact, or immediately during impact, the force increases sharply, and as time progresses, what happens to the force? The force decreases. Normally, this value should be the maximum force. This is the maximum force on the body, and this is at the average time, T average. So that is how the graph will look like. The graph will look like this, a graph of force against time. So that said, let's proceed to question 3. Now, question 3a, explain what is meant by a thermometric property. Okay. B, the table below shows the specifications of some common thermometers. We have been given the thermometers in column 1, their property in column 2, and the uses or advantages in column 3. So we have to identify A right up to E. Okay. So in A for the first thermometer, what I've given us the property, and they say the property is the change of mercury thread with temperature. So I have to identify A and B for the first thermometer. So okay, so 3A, they're asking us what is the thermometric property. What I will say is this: a thermometric property is simply any physical property of a substance that varies linearly with temperature and can be reproducible. Normally, it is always constant at particular temperatures. Okay, so if I was to write this down, I'll say a thermometric property is any physical property of a substance that varies linearly with temperature and is reproducible. Normally, this property should give precise values at particular temperatures. Okay, so in B, we are to fill this table. So for the first column, for the first row, they have given us the property and they're asking for the thermometer and the use. Okay, so since different thermometers exist, and these thermometers are so differentiated based on their thermometric property, so telling us that the thermometric property is the change in mercury thread of the thermometer, I will quickly say that A is a liquid in glass thermometer. So we can have the liquid could be mercury or could be alcohol, and it is the length of the mercury thread or the length of the alcohol thread or stem. Okay, so as for the use, one advantage that a liquid in glass thermometer has, or mercury thermometer has, is the fact that it is portable. It is not heavy. You can carry it from place to place. And secondly, it is easy to read because normally the glass strand is transparent. Since it is transparent, you can easily pick values, and equally mercury there, the mercury is colored. Okay, that's one advantage of mercury that enables it to be used over water, to be used in the place of water for us for a thermometric property. So I'll say B. I'll say it is easy to read, and this is particularly because mercury is colored. The mercury in the thread is colored. Secondly, another property that works well for B or use is the fact that it is portable. It is portable. Can easily be carried from place to place. So that was for the first thermometer, C. Now, for the second thermometer, C, they have given us the use, and they say it is used to calibrate other thermometers. Normally, there are so many thermometers, as we will see. liquid in glass, constant volume, bimetallic strip, electrical resistance, or platinum resistance, thermocouple. There are so many thermometers that exist. Among those thermometers, there's a particular one which is the constant volume gas thermometer. It is used to calibrate other thermometers. Take for instance, you can use a constant volume gas thermometer to calibrate a liquid in glass thermometer. That is in the case of using alcohol as the thermometric property, or as a thermometric liquid. So here in C, I will say C is a constant volume gas thermometer. A constant, these things are not there. A constant volume gas thermometer. Now, D needs the property. As for the property we have, since we're dealing with gas, the property will be the change in the pressure of the gas. The change in the pressure of the gas. So we have change in the pressure of the gas. And take note, most of the times we use ideal gases. Now, in E, they've given us two things. They've given us the name of thermometers and the use or advantage. So you see, thermometer is a platinum resistance thermometer. The advantage of the use, it is accurate and sensitive, or can measure high liquid temperatures. Okay, so asking for the thermometric property, I will say thermometric property for E is the resistance of the resistance of the wire. In this case is the resistance of the platinum. So we have resistance of the platinum thermometer. The resistance of the platinum, this is with temperature. Okay, so that's it for question 3.